Okay, this is going to be the replacement lecture for the slide material on Chapter 9 because my computer wasn't working that evening, which was last Tuesday. So here it is, Chapter 9, which is the first of two chapters on energy. In this chapter, we're going to talk about work and the work kinetic energy theorem and sort of energy in general. Okay, so as it says, we're going to begin the study of how energy is transferred and transformed. Okay, so he likes to think about things with a box. And the reason he wants to think about it this way is that he's thinking of it in terms of a conservation principle. That is, as far as we know, one of the great conservation principles of the universe is the conservation of energy. As far as we know, the energy of the entire universe is a conserved quantity. That means it doesn't change. Okay, well, if you have a small part of the universe, like for example your system, it can have an energy change, and the way it can have an energy change, as you see here, is that the environment can put energy in and the system itself can transfer energy out. And we're going to see examples of that. Okay, there are many different kinds or forms of energy. Kinetic energy and potential energy are the two sort of big buckets that we're going to put them in. Kinetic energy is energy of motion. So if something is not moving, it has no kinetic energy. But if something is moving, it does have kinetic energy. And we will learn a formula for that, 1/2 mv squared, which is correct in the non-relativistic limit. Potential energy, on the other hand, is energy of position. And what does that mean? Well, that means that it has that energy just by virtue of where it is. Okay, so its state in terms of position in the universe gives it potential energy. Thermal energy is actually a kind of kinetic energy. As it says right here in the slide, it's the energy of random motion of atoms within an object. So those atoms are jiggling around, and that's kinetic energy because they're in motion. But we're not interested in the individual details of the motions of all the different atoms and the electrons and protons and so on inside that atom. So we just sort of lump it into, oh, well, thermal energy. And we experience that as heat. In any case, all kinds of energy have the same units. They're measured in joules. We'll talk about that in a little bit. Okay, work has an unfortunate name because, of course, we use the word work to mean something you get paid to do. But that's not what we mean at all when we're talking about it in physics. Work, we mean something extremely specific in physics. What we mean is a force integrated over a displacement. Okay? So if there's no displacement, there's no work. So for example, I could stand in front of you holding a heavy book and my muscles would be straining. But as long as I am not moving, the book is not moving, I'm exerting that force to hold the book up, but there's no displacement of the book, so there's no work done. Okay, so we have to distinguish between what we mean in the vernacular by work and what we mean in physics. Okay, as we said just a minute ago, the basic idea is that energy of a system can change because energy can flow in, energy can flow out. And in fact, also the type of energy inside the system can change. And we saw that earlier here with the different kinds of potential energy and kinetic energy. We're going to see that potential energy can be transformed to kinetic energy, and either one can be transformed to thermal energy, and so on. We'll see examples of that later on. But the basic idea in this slide is the work kinetic energy principle, which is that the change in the energy of a system is the external work. Okay, and we're going to also see, well, we'll see that later. Okay, the last idea in this chapter is the idea of power. And power is the derivative of energy with respect to time. So it's the rate at which, the time rate at which energy is transferred or transformed. Okay, so we've already done the reading questions for homework, so let's just speed through that and get right to the first slide, which is sort of the energy overview, all right? Moving objects have energy. Energy is the ability to make things happen. If you have a heavy object held over your head and somebody drops it, it has the potential to give you a bump on the head. So that's a kind of potential energy, da 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 da. All right, so first off, let's talk about kinetic energy. It's the energy of motion. All moving objects have kinetic energy. The more massive an object is, and the faster it moves, the larger its kinetic energy. We also have potential energy. That's the energy of position. We think of it as stored energy because it took energy to put it in the position, but now that it's in that position, it has the ability to do work. So for example, if you have a pile driver, it takes energy to raise that heavy weight up, but then once it's raised up, just by letting go, you can get energy and you can get work done. You can actually drive the stake into the ground or whatever. Thermal energy is the energy that we experience as heat, and you can see this this horseshoe here is glowing, and the reason it is glowing is that the molecules and atoms in the horseshoe are moving very rapidly, and they're actually radiating visible light. So, okay, so here's the basic idea. There's this box around the system. We can change the energy of the system by putting heat in or by putting work in. This will add energy to the system. We can also remove energy from the system. We can remove heat from the system. We can also make the system do work on the environment, and that will make the energy of the system go down. You can also change the kind of energy inside the system. So kinetic can become thermal or potential or chemical or atomic. I mean, there are lots of kinds that we're not even listing here. So in this course, we're just going to be talking about kinetic and potential and thermal, though. So this chemical is sort of beside the point. Okay. All right. So for example, here's an energy transfer example. This athlete here is putting a shot. He's got a heavy ball in his hand, and he's going to use his arm muscles to make the shot go away. That is to foosh the shot away from him. Right. So he's doing work on it. That is, he's exerting a force over a distance to give the shot put kinetic energy. Or you can also do a similar thing by pulling this elastic back. Pulling the elastic back takes effort, right? So you're exerting a force over the distance of pulling this elastic back, right? So that's work that you're doing, and that's going to become the potential energy stored in this rubber band. So there you are. The diver is falling off a cliff, okay? So, oops, sorry about that. The diver is falling off a cliff, so that the diver had gravitational potential energy when standing on the cliff, and then he just sort of falls off, and as he falls, he speeds up. How does he get the kinetic energy of speed that he's acquiring by speeding up there? Well, he's transforming his gravitational potential energy, that is his energy of position at the top of the cliff, into kinetic energy, energy of motion. Here's a speeding meteor, and as it comes through the atmosphere, it slows down. It radiates heat by being slowed down by the molecules of air in the atmosphere. And so it's transforming its kinetic energy of motion into heat energy of heating up itself and the air molecules. Okay, so the basic idea of energy in general is that you can transform one kind of energy into another kind of energy. You can also transfer energy into the system or away from the system. But if we treat incoming energy as positive transfer and outgoing energy as negative transfer, with work being the only energy transfer process that we're considering right now, then we can write that the energy of the system changes only due to work done on the system by the environment. Okay, so here's that basically energy model, da 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 da. Notice that the system can transform different kinds of energy within itself. You can also do work on the system. That would be positive work. You can make the system do work on the environment. That's negative work on the system. So that removes the energy from the system. So we speak of that as negative work because it reduces the amount of energy in the system. Okay, so here we have some simple examples. We've got a skier gliding down a slope at constant speed. Okay, if he's going at constant speed, then that means his kinetic energy is not changing because his speed is constant. So he can't be either gaining or losing kinetic energy. But he's going down the slope, okay? So that means he's losing potential energy because he's going downhill, okay? So where is that energy going? And if you said that, well, if he's going at constant speed, there must be friction, you were right, okay? There is friction acting on the skier, and therefore there's thermal energy being produced. So there's the correct answer. He had gravitational potential energy, and he's heating up the snow in his skis. All right, let's talk about the work kinetic energy principle for a single particle moving in one single dimension, which he's now calling here S instead of X, well, whatever. All right. So if there's a force in the same direction as the direction of motion, then that must be either speeding up or slowing down, not changing direction. And if it's in the exact same direction as opposed to opposite direction of motion, it must be speeding up. And we found this out way back in chapter 2. So we can see that the force in the direction of motion leads to the velocity arrow, this green thing here, getting longer. So that means that the system has increased in kinetic energy. Well, what is that? Well, the kinetic energy is defined as 1/2 mv squared. And we're going to find out why that's a good definition in a little bit here. But for right now, let's just look at this equation and see if we can understand it a little bit. All right. Now, the K here, as I say, stands for kinetic energy. There's a 1/2. M is the mass of the system, and V is the speed of the particle. Notice that this is not the velocity of the particle because it's squared, okay? So this is like the velocity dotted into the velocity, which gives you just a scalar number here. Kinetic energy, like any kind of energy, is not a vector, it's a scalar. So notice that also that it depends on the square of the speed and only linearly on the mass. Also notice what the units of kinetic energy have to be. Like the units of any kind of energy, they have the same units, obviously. Otherwise, you couldn't transform one into the other. It would be impossible if they didn't have the same units. We have a special name for the unit of energy. We call it a joule, right? And we use the symbol J. And you can read off what those energy units are, what the joule is, just from this definition of the kinetic energy. It has to have the same units on both sides of the equation, of course. So the units of joules must be the same as the units of mass, which is kilograms, times the square of the units for velocity, which is meters per second. So this is kilogram meters squared per second squared, and that's right here. Okay, so ball A has half the mass and 8 times the kinetic energy of ball B. What is the speed ratio, VA over VB? Well, if it has half the mass, but 8 times the kinetic energy, then it must have 16 times the V squared. Well, if V squared is 16 times, then V is 4 times. Okay, so let's look at our definition of change of kinetic energy here. Remember, change in anything is the final minus the initial. And what we're going to say is that our general work kinetic energy theorem is that the net work done, the total amount of work done on a system must equal the change in the kinetic energy. Okay, so here we are. Here is the work definition. It's the integral of the force over the displacement, just what I told you in the introductory slides. So in this particular case, it's a constant force parallel to the direction of motion, which is the s-axis. So if it's a constant, I can take the fs outside the integral, right? So notice it's outside of the integral here. It's a constant with respect to the integration, so I can take it outside. And then I've just got the integral of ds. But I know what the integral of ds is by the fundamental theorem of calculus. That's just s evaluated between the limits, s final and s initial. So that's F sub S times delta S. Delta S, remember, delta of anything is the final minus the initial. So that's so the work done in this case of a constant force parallel to the direction of motion is just F sub S times delta S. Notice that the unit for W, the SI unit for W, is also a joule. How do you know that? Well, we've got the units of force, which are newtons, times the units of distance, which are meters. So a newton is a kilogram meter per second squared. So if you take a kilogram meter per second squared and multiply it by meter, you get a kilogram meter squared per second squared, which is exactly what we saw in the previous slide, 2 previous slides, for the joule. So that's correct. And if it weren't the same units as kinetic energy, we'd be very upset because there'd be no way we could say delta K was equal to W unless they had the same units. That wouldn't make any sense. Okay, let's talk about the sign of work. As you know, integrals can give you a negative result. Well, work can be either positive or negative, and we mentioned that before. If the force causes the particle to speed up, then the work done by that force is positive. That is, we're putting energy in, right? That is, the final kinetic energy is actually bigger than the initial kinetic energy. And remember, the delta K is always the final minus the initial. So if final is bigger than initial, then this is a positive number here, which means the work is positive. On the other hand, if initial is bigger than final, then this is going to be a negative number. And if it's a negative number, then that must mean that it's slowed down. And you can see that here in the pictures. Here's the work. Here's positive work because the force is in the same direction as the velocity, and so it speeds it up. Here's the force, the red arrow, in the same direction as in the velocity, so it speeds it up. Here, on the other hand, the force is opposite the direction of the velocity, so that means that the final velocity arrow is shorter than in the initial velocity arrow, and so the thing is slowing down. This is negative work. Okay, what if the force is constant but not in the same direction as the displacement? Well, then only the amount of the force that is in the direction of the displacement is going to actually do work. And that's what we meant by F sub S, the amount of the force arrow that's in the direction of the displacement. All right? We use that same notation here. But we said that the force was, in fact, parallel to the displacement, so all of the force was in the S direction. But now we're considering a case where some of the force is not in the S direction, but some of it is. And you can see that the projection of the force arrow onto the axis for the displacement, there's a non-zero amount there, and you can just take the amount of the force that's in that direction, which is the length of the hypotenuse, F, times the cosine of this angle theta, and that gives you F sub S. So we have the same equation for W. W is equal to the integral of F sub S ds, but now we have to actually take only part of that force, which is F cosine theta. Okay, in the previous example, it was the same thing except that the theta, that is the angle between the force and the displacement, was 0. And as we know, the cosine of 0 is just 1. So this reduces to the same equation. Okay, so if we have a constant force, again, we can take the F outside the integral. We can certainly take the cosine theta out of the integral if the angle doesn't change here, because that doesn't depend on the integration variable. So we can take all that stuff outside the integral in this special case where it's constant strength and a constant direction. And then again, we have the integral of ds, and again, of course, by the fundamental theorem of calculus, that's just delta S, or delta R, they're calling it here, just to make it confusing. Okay, so here is a physical example where you can see that the force would naturally be at an angle to the displacement. We've got a suitcase on a strap, and because we don't want to crouch down next to the suitcase and pull it horizontally, instead we want to use our strap and just pull at an angle here. It's easier. So that means that our tension force on the strap is not the same direction as the displacement. The displacement of the suitcase is along the x direction, but only the amount of the force that we are exerting that's along the displacement is going to do work. Now suppose that, as in this example, the angle is 45 degrees. Then we would take the amount of force T, we'd multiply it by the cosine of 45 degrees, and then we'd multiply that by the displacement here of 100 meters, and that would be the work done by the tension. Okay, we've got a crane lowering a girder into place at constant speed. We want the work done by gravity and the work done by tension. Well, if we imagine doing a free body diagram of the crane, the work done by tension and the work done by gravity, those are done by two different forces. Gravity points downwards and the cable tension points upwards. Okay? The crane is lowering the girder into place. So notice that the displacement is downwards. Okay? Which direction is gravity? Gravity is also downwards. So the angle between the gravity force, which is downwards, and the displacement vector, which is also downwards, the angle between those two arrows is 0. So the cosine of 0 is 1. So the work done by gravity is going to be positive. However, the work done by tension is going to be negative. Because why? Because the tension is upwards, but the displacement is downwards. So the cosine of 180 degrees is -1. So the correct answer here is that the work done by gravity is positive and the work done by tension is negative, and that's B. Okay? All right. So here are lots of different possibilities. Okay? First off, we've got the force and the displacement. The force is in the red arrow and the displacement is the blue arrow. Notice that the force and the displacement arrow are exactly the same direction. So the angle between those two arrows is 0. And so the work is F times delta R, and that's a positive work. Okay? And notice that energy is transferred into the system. The particle is speeding up. As we know, if the force and the velocity are in the same direction, that means we're going to speed up. That means our acceleration, which is in the force direction of the force, is in the same direction as the velocity. So that means we speed up. This is stuff we learned in chapter 2. So we understand this one very well. All right, let's look at this one. Now we've got a force at an angle theta to the displacement, but there's still a component of the force that's in the direction of the displacement. So part of this force arrow does work. You can see that that's that amount of the force which is in the direction of the displacement. So it's going to be a positive work done, but it's not going to be as much as in this case. And you can see that the increase in the velocity arrow is actually less in this case because less of the force is doing work. Okay, let's now look at this example. All right, we've got the force making a 90-degree angle to the displacement. In this case, the force does no work at all. Okay, because why? Because there's none of it in the direction of the displacement. So if I take F times cosine theta, well, cosine of 90 degrees is 0. So that's going to be 0, right? So there's no force that's in the direction of the displacement. So that means that the work done is 0. That means that the particle does not speed up. At most, it changes direction. I mean, in this case, they're not even showing that it's changing direction, but it ought to. All right. What if the angle theta is bigger than 90 degrees? Well, in that case, you can see that the projection of the force arrow along this axis actually gives you a negative number. This amount of the force here would be an opposite to the direction of the displacement. So that means that the work is actually negative because it's going to be slowing the particle down. The most slowage downage, of course, would be if all of the force is in the negative direction. That's if the theta here, the angle between the displacement and the force, is 180 degrees. And then the cosine of 180 degrees, of course, is -1. So we're going to get negative work done, and we're going to have maximum slowage downage. Okay, let's do a few simple examples and see if we understand this. So Robert is pushing the box to the left at constant speed. Okay. What are all the forces on the box? Well, there's clearly gravity. There's clearly normal force from the surface, the floor that it's sitting on. And since Robert is pushing on it, there must be a force in this direction, the push direction. But if the box is going at constant speed, there must be a force going that way. I would guess that that would be the frictional force coming from the surface here. So the frictional force would be opposite. And since the box is going at constant speed, that means that this force and the push force must exactly cancel because there's zero acceleration of the box. Okay, now that we've done the free body diagram, at least in our heads, let's talk about the work. What is the work that Robert does on the box? Is it going to be positive, negative, or zero? Well, we can see that the force is this direction that Robert is pushing with, and the displacement is also in this direction. Okay? Therefore, the force and the displacement are in the same direction, so it must be positive work. The correct answer is A. Okay, here we have a slightly more abstract example. We've got a constant force pushing a particle through a displacement delta r, and in which of these three cases does the force do negative work? Okay, so is there a component of the force in the negative delta r direction? Or equivalently, is there a component of delta r in the negative f direction? And you can see that in case A, that's certainly the case. In case B, that's certainly the case. But in case C, F and delta R are in the same direction. So in case C, that's going to be positive work, but it is going to be negative work for A and B. Okay, here's another physical example. We've got a rocket being launched straight up. The rocket motor generates a thrust, and we want the rocket speed at a height of blah. Okay, so here's the rocket. Here's the before picture, the after picture, and here's the free body diagram. There are only two forces on the rocket. We're ignoring air resistance. So there's the gravity force and there's the thrust force. So clearly we can see that the thrust force is doing positive work. Why? Because the thrust force and the displacement of the rocket are in the same direction. Gravity, on the other hand, is doing negative work. And you can see that because the gravity force is in the opposite direction from the displacement. So remember, the change in the kinetic energy is going to be the net work done on the particle. So we have to take the positive work that's done by the thrust and add it to the negative work that's done by gravity to get the net work that's done. And then that's going to equal the change in the kinetic energy. So let's see what they do. All right, here's the work. Oh, sorry about that. Here's the work done by the thrust force. That's the size of the thrust force times delta R. Right? Because why? Because they're both in the same direction. So we can actually calculate that out. We're given what the thrust force is, and we're given what the delta R is. So there it is. 2 times 10 to the 9th joules. 2 billion joules. That's a lot of joules. All right. What about the work done by gravity? Well, as we just said, the force and the displacement in the case of the gravity are in opposite directions. So that's going to be negative. So we've got the force times the displacement times the cosine of 180 degrees, which is -1. So that'll be minus mg times delta R. And so we can write that down too, and we get minus 0.74 times 10 to the 9th joules. So the net work is 2 minus 0.74 times 10 to the 9th joules. And that's got to equal the change in the kinetic energy of the rocket. So here it is. Change in kinetic energy, which is the final minus the initial, must equal the total or net work done on the particle, which is the sum of those two works, one of them positive and one of them negative, and that's 1.26 times 10 to the 9th joules. Now, how do we find out the speed? Well, we find out the speed because the change in kinetic energy is equal to 1/2 mv final squared. So just put in what the, multiply through by 2 and divide through by the mass and take the square root, and you get this. Okay, which force below does the most work? All three displacements are the same. Right? Well, you can see that in this example, the force and the displacement are perpendicular to each other. So this force has no component in the direction of the displacement, so it can't do any work. So the work done here is 0. Right? So alternative A and alternative D are garbage. Right? Now let's look at this one. This is 8 newtons, but it's at an angle. All right, so the amount, you have to take the amount of this force that's along this direction. So that'll be 8 newtons times the cosine of 60 degrees. So 8 newtons times the cosine of 60 degrees is 8 newtons times 0.5, or 4 newtons. So this will be 4 newtons times delta R will be the amount of work. What about this one? Well, this is along the same direction as the displacement. So this is 6 newtons times that same delta R. So I would say this one does the most work. So I'm going to go with C. Yay. Okay. We've got a light plastic cart and a heavy steel cart, both pushed with the same force for a distance of the same 1 meter starting from rest. And we want to know what the final kinetic energy of each of those two things is compared with each other. Well, if we've got the same force pushed over the same displacement, it's got to be the same change in kinetic energy. All right, so I'm going to say that they're exactly equal. Okay. On the other hand, if we asked a different question, if we asked which one's going faster, we'd have to say that the light plastic cart is going faster. Because why? Because it has a very small m. This guy has a very large m. We've got the same final kinetic energy. 1/2 little m, big V squared. And this is 1/2 big M, little v squared. Right? So I'm going to say these are equal. All right, let's talk dot product. All right, so what's the dot product? Well, the first definition of dot product that we're going to use is that the dot product of A with B is the magnitude of A times the magnitude of B times the cosine of the angle between them, also called a scalar product. All right? Make sure that we're using the angle that's between those two vectors. And notice the notation here. Notation is very important. If you've got an arrow over the top, then that means it's a vector. Arrow over the top means it's a vector. Without the arrow, all it means is the magnitude. So you can't label this arrow B magnitude. That would be wrong. You have to label it B with a vector hat on it, B with a little arrow over it. But in this right-hand side of the equation, we have magnitude of A, magnitude of B, cosine of alpha. So this right-hand side of the equation is a scalar, right? That's why it's called a scalar product. Magnitude, magnitude, and just number. Well, so when you take the dot product of A with B, you get a number, okay? That reduces this product of these two vectors into a number, a scalar. Okay, so what it means graphically is the projection of the one arrow onto the other. It doesn't matter which one. You can project A onto B, B onto A, exactly the same, because A dot B equals B dot A. And you can see that right here in the definition. Because if you wanted to write down what B dot A was, well, that would be the magnitude of B times the magnitude of A times the cosine of the same angle alpha, right? And since, arithmetic doesn't care if you say magnitude of A times magnitude of B or magnitude of B times magnitude of A, it obviously has to be the same thing. Okay, here are some pictures that'll give you a feel for this. Here, A and B are pointing in the same direction. In other words, the angle between them is 0. So that's AB cosine alpha, but alpha is 0, so cosine of 0, which is just 1. Right. Here we have alpha less than 90 degrees. Okay, so we've got cosine of alpha, which is going to be a positive number. So we get magnitude of A times magnitude of B times a positive number, which is the cosine of alpha. Here we have magnitude of A times magnitude of B times cosine of 90 degrees, but cosine of 90 degrees is 0. So here we get 0. And geometrically, you can see why, because if you try to project A on B, you get 0. There's no component of A that's along the B direction. There's no component of B that's along the A direction either. In these two cases, we're going to get a negative number. Not because the magnitude of A or the magnitude of B is negative. Magnitudes can't be negative, but because of the cosine being negative. The cosine of an angle greater than 90 degrees is a negative number. And you can see why, geometrically, because if you try to project A onto the line of Bness, you can see that that amount of A is pointing in the opposite direction from B. And similarly, if you've got 180 degrees here, you can see that A and B are exactly diametrically opposed. In other words, A dot B is minus A times B. That is minus the magnitude of A times the magnitude of B, because the cosine of 180 degrees is -1. Okay, so here we have a simple, easy example. The magnitude of A is 3 in some units. Magnitude of B is 4 in some units. So we have 3 times 4 times the cosine of 30 degrees for the dot product. Okay. You can also write that the dot product is the sum of the products of the components. And the reason you can do this is that when you write A out in its components like this and B out in its components like this, and then dot this expression into this expression, that's the same as this times this. Well, now it's this times this, plus this times this, plus this times this, plus this times this. But when you dot I into I, that's the component of I along I, well, that's just the number 1. Similarly, the component of j along j, that's also going to be 1. But the component of I along j is 0 because the angle between the I unit vector and the j unit vector is 90 degrees. So we don't get 4 terms multiplying this sum times this sum. We only get 2 non-zero terms, this times this and this times this. And that's what it says down here. Okay, so here's another example. Calculating dot product using components. Since we're given A and B as components, we can just multiply them together. So A dot B is going to be 3 times 4 plus 3 times minus 1. All right, 3 times 4 plus 3 times minus 1. Oops, sorry about that. There we are. All right, now let's apply that to the work done by a constant force. We can take the component of F along the displacement just by writing the two of them as vectors and taking the dot product. That will get the component of F that's along the displacement direction, the thing that we were calling F sub S earlier. Okay, so, sorry, here's a numerical example. We've got a skier gliding at 2 meters per second when he starts down a very slippery slope. Very slippery, okay, code word for no friction, fine, we understand that. We want to know the speed at the bottom. Well, if we're given his initial speed, and we want to know his final speed, that sounds to me like they're trying to get us to calculate a change in kinetic energy. Here's our initial speed, here's our final speed, and we're given the mass. So if we can figure out what the change in kinetic energy is, we can figure out the final speed. Okay, so now what we have to do is calculate the change in kinetic energy. But we know that that's equal to the net work done on the skier. Okay, so let's do a free body diagram of the skier and find out what all the works done by all the forces on him are. Okay, or her, or whatever. All right, so remember we're saying that there is no friction. So there are only 2 forces on the skier. There's the gravity force directly down towards the center of the Earth, and there's the normal force directly normal to the surface of the slope. Notice, though, that the force that from the normal force of the surface is at 90 degrees to the displacement. That means that if I took this force and dotted it into the displacement, I'd get 0. So the normal force does no work. The only work done is done by the gravity force, because that's the only other force, and this guy does no work at all. Okay, so what we need to do is dot this force into this displacement, and that's going to give me the net force done, the total work, the total work done, the net work done, and then that will equal the change in the kinetic energy. So here it is. The work done is the gravity force dotted into the displacement delta r, which is mg delta r cosine of the angle between them. And this angle they're giving us as 80 degrees. So that gives us the work done, and it has to be the total or net work done because this is the only other force and it doesn't do any work. So therefore it must also equal the change in the kinetic energy. So that's what we see on this slide. Remember, change in anything is always the final minus the initial. So we rearrange this equation to get the final speed, which is what we wanted to know, and there it is. Okay, there are also many cases where there are 0 work done. Okay, for example, what we saw earlier, when we saw earlier that there was a normal force acting, but the normal force did no work, that was because the normal force was at right angles to the displacement. But there are other situations where where there's a force that's at right angles to the displacement. For example, Suppose you have a particle going in uniform circular motion. Well, if it's going in uniform circular motion, remember that means constant speed in a circle, okay? We have to have a net force towards the center of the circle, or it doesn't go in a circle, but that force towards the center of the circle is always at right angles to the displacement. The displacement is always tangent to the trajectory, and the force is always perpendicular to that tangent direction. So therefore, the force that's making it go in a circle does no work. All right, so here we have another example. We've got a car on a level road turning a quarter circle counterclockwise. Okay, we know that it's static friction that's making it go in a circle. In other words, the net force towards the center of the circle that makes it go in a circle is provided by the static frictional force. Okay, so what is the work done by static friction? Well, we just found out that a centripetal force, the force that makes you go in a circle, can't do any work. Why? Because it is at right angles to the displacement. So I'm going to say that the work done by static friction here is 0. Yay! All right. Here's another example of 0 work done. Here's a skater pushing off a wall. Why is there 0 work done in this case? Because there's no displacement, like the example of my holding a heavy book in front of the class that I cited earlier. Okay, what about if the force that we're interested in is not constant? Okay, there are examples where there's a constant force. We've been talking about those all along. But what if the force that we're interested in is not a constant force? Well, in that case, we have to actually do the integral. Okay, remember we started out with this formula, but then in each case where where the force was constant, we could take the force outside the integral. Well, if the force is actually dependent on the variable of integration, then we can't take it outside the integral, obviously. But we can still do the integral in many cases, and in any case, geometrically, it's the area under the force versus position graph. Okay, so here are some examples. Come on, you can do it. There we are. All right, so here we have an example of a tow force on a car, right? And this graph is showing the force as a function of distance x, right? And we want to know what the car's speed is at the end of that 200 meters. Well, we can figure out the work done by the towing force just by taking the area under this curve. So this is the area of a triangle, which is 1/2 the base times the height. And that gives us the work done by the towing force. And then, of course, the net work has to equal the change in the kinetic energy. So that's what they're doing here. Okay, another really important example is the spring force that we've discussed before. If you stretch a rubber band, a force tries to pull the rubber band back. That's a restoring force, it's called. Okay. If you stretch or compress an elastic object like a spring, then the force provided by the spring is opposite to the displacement. If you stretch the spring wants to get back to its unstretched length, so it pulls in that direction. If, on the other hand, you compress the spring wants to get back to its unstretched length, so it pushes outwards. Okay, so the model that we're going to use for most of our spring problems is Hooke's law, which is that the force is linear in the displacement. Okay, so, here's Hooke's law. It says that the spring force is opposite the direction, that's the minus sign, to the displacement delta S. And the spring constant K here is the slope of this line, right? So K would be larger if it were a very stiff spring and smaller if it were a very weak spring, like a rubber band or something like that. Okay, so for example, here we have the spring force as a function of delta x, and notice that they're doing this, they've taken the absolute magnitude here. So instead of showing you the correct sign here, they're just taking the absolute magnitude, but never mind, doesn't matter. All right, so These are three different curves of spring force as a function of delta x. This is the steepest one, so therefore that's the one with the stiffest spring constant. It's the stiffest spring. Okay, so here we have another numerical example. Pull till it slips. We've got a spring attached to a block. The other end is pulled by a toy train that moves forward at blah. And and we've got a spring constant. All right, so we want to know when the block starts moving. So what we've got here is a block, which we're going to do a free body diagram of the block, and it's attached to a spring. And the spring is going to create more and more and more force on the block until it moves. How do I know it's going to create more and more force on the block? Because the train is pulling the spring out, thereby distending the spring more and more and more, therefore increasing the spring force more and more and more until the block finally starts to move. So what we're going to do is do a free body diagram of the block. So here's the free body diagram of the block. Here's the gravity force downwards. Here's the normal force from the ground upwards. Here's the spring force this way. And here's the static frictional force from the table that way. Now, when will it start to move? It will start to move when F sp just is a little bit bigger than Fs max. And we have a formula for Fs max. We know how the biggest that a static frictional force can be is equal to mu s times n. And we can figure out how big n is by doing a Newton's second law in the y direction. So that's what he's going to do on the next slide. Oh, well, all right. That's what he's going to do, right? So here's the sum of the forces in the x direction, which is the spring force minus the static frictional force. And if it's at equilibrium, then that's going to equal 0. Now, the point at which this is maximum is the force at which it just starts moving. So we're going to say that that's going to be the point at which Fs equals k delta x, and that's when Fs max equals mu s n equals mu s mg. All right, so there that is. Okay, earthquakes are another example of stick-slip motion, which is kind of cool. Well, whatever. All right, let's talk about work done by springs, right? So remember that when you've got a force that is not constant, you can't take it outside the integral sign. On the other hand, we know perfectly well how to do this kind of integral because we're doing an integral over the displacement, and we know that the spring force is just linear in the displacement. So all you got to do is just integrate s ds, and you can do that. You get s squared over 2. So that's where we get that the work done by a spring is 1/2 k x squared. All right, let's talk a little bit about thermal energy, dissipative forces, and thermal energy. As I said earlier, thermal energy is just the way we're going to sort of sweep under the rug all the details of the microscopic motions of all the atoms and molecules inside a solid, because we're just not interested in it, and we certainly don't have the time to waste figuring out Newton's equations of motion for billions and billions and billions and so on of atoms. So we're just going to call that heat, the great graveyard of energy where eventually all energy goes. So we're going to call that thermal energy. All right. So let's see how that we would apply that in a particular physical application. We've got a tow rope pulling a skier up the slope at constant speed. Now, if it's constant speed, his kinetic energy is not changing. Okay. On the other hand, if we're pulling the skier up the slope, right, we have to be giving him potential energy, right? Because he's going from a lower gravitational potential to a higher gravitational potential. So we must be exerting a tension force on him, which does work and gives him gravitational potential energy. Okay. There may also be thermal energy going on here as the skis and the slope are heated up. So this is not a very well worded question, but I'm going to say that we've got both A and C going on here. Yeah. All right, so where does that come from? Well, it comes from the fact that no surface is completely smooth, and every single scrapage of one surface over another is going to mean that we get some pushes and pulls between the atoms in the one surface and the atoms in the other surface. It's a dissipative force because it means that energy is lost to this great graveyard of energy idea. That is the microscopic motions of all the particles. The reason that it's lost is the second law of thermodynamics, which you may or may not have hit already in chemistry class, but in any case, there it is. Okay, so we're going to calculate the work done by a frictional, therefore dissipative force in exactly the same way as we calculated the work done by all these other forces. How do we do that? Well, we've got the force and we dot it into the displacement. Here's the displacement in that direction, and here's the force of friction in that direction. Notice that's going to be negative work done on the system. In other words, the friction is going to slow the system down. The way it does this is by increasing the thermal energy. Dissipated forces always increase the thermal energy. Okay, so here we have an example. We've got a rope with particular tension on it, and it's pulling a 10-kilogram crate 3 meters across a horizontal floor starting from rest. Coefficient of friction is blah. What's the increase in thermal energy? What's the crate's final speed? Okay, so we've got to do a free body diagram, okay, of the crate. We've got to put in all the forces on the crate. We've got to figure out how much work the tension does. We've got to figure out how much force, how much work the friction does. And then we can figure out what the net work, the total work done is, and therefore get the crate's final speed. So the increase in thermal energy is going to be a decrease in energy of the crate, decrease in kinetic energy of the crate. Okay, so that's the energy principle there. So it's very easy to figure out the change in the thermal energy because the friction and the displacement are along the same direction, so that's just mu k mg delta s, just as we saw earlier, and they've just figured this out for us. That's 59 joules. But we also know that the tension is 30 newtons, and it's pulling it 3 meters across the floor. So that must be doing 30 newtons times 3 meters of work. Well, that's 90 joules, okay? 90 joules of work, of positive work that the tension did, okay? So we have to subtract this 59 joules to get the net work done on the crate, and then that will give us the final kinetic energy, or the change in kinetic energy, therefore the final speed. So there it is. The tension force does the 90 joules. 59 goes to increasing the thermal energy. So the change in kinetic energy, which is the net work done, is 90 minus 59, or 31 joules. So then we can get the final velocity. Okay, the last thing we're going to be talking about in this chapter is the idea of power. Remember, power is defined as the time derivative of the energy. Okay, so it's dE dt. The unit, the SI unit that we're going to use to deal with this is the watt. This is the SI unit of power, and it's defined as a joule per second. Notice that that's correct, because if this is in watts on the left-hand side, then the numerator here must be in joules. A small amount of joules is still a joule. dE must be in joules, and dt must be in seconds. So we get joules divided by seconds, or joules per second, which is a watt. Some problems that you're going to be working with are also going to be using horsepowers. Horsepowers are defined as 746 watts. I don't know how they got a standard horse, but apparently they did, and that's 746 watts is one horse. Whatever. Okay, so here's some examples of power. Here's a light bulb. It's 100 watts. It's rated as 100 at 100 watts. That means that the amount of power that it puts out in terms of both light and thermal energy is 100 joules per second. Here's an athlete. He's rated at a half a horsepower. Goodness knows why. Here's a gas furnace rated at 20,000 watts. Okay, fine. All right. Power is the dE dt, but remember, work is also a kind of energy. So you can also think of power as dW dt. Well, how do we get what dW dt is? Well, remember that if the force is constant, W is just F times delta X. And if we ask for d by dt of F times delta X, remember if the force is constant, we could take the F outside. So that's F times dx dt. Well, dx dt is just V. So that's F times V, right? So there's another way of writing what the power is. Don't worry, it's on your formula sheet. All right, let's just do this one quick check here. We've got 4 students running up the stairs in the time shown. We wonder which student has the largest power output. Okay, so let's just compare them in pairwise. All right, so let's look at A versus B. In A and B, we both have an 80 kilogram person going up 10 meters, but A takes 10 seconds to do it, and B does it in a shorter time. So B is clearly the higher power, right? B is bigger than A. Now let's look at C. Let's compare B with C. Well, B and C have the same time, but the amount of energy is less because for C. The amount of energy in C is less than the amount in B because B has 80 kilograms and C only has 64, right? So I'm still going to say that B is bigger than C. All right, now let's compare B with D. We have the same mass as B and D, right? But in D, they're going up twice the height, but they're taking over 3 times the time. So multiply by 2 but divide by 3, so D is still less than B. So I'm going to go with B as the largest one. And in fact, we're correct. Yay! Okay, here's another numerical example from your book. We've got power output of a motor. We've got a motor and cable to drag a machine to the proper place on the factory floor. What power must the motor supply to drag the machine? And we can figure this out because we know we can figure out what force it needs to do, and we're given what the speed needs to be. So that gives us the power. If we can figure out the force, we can just multiply that by the speed, and that gives us the power. Okay, so how do we figure out what force is necessary? Well, we do our free body diagram. Remember, that's almost always what we do first of the machine. So tell me all the forces on the machine. Well, we've got gravity downwards towards the center of the earth. We've got normal force upwards. We've got the tension force of the cable, and we have kinetic friction backwards. Okay? So that means that the net force must overcome this frictional force as well, right? So that means that the power that's needed, the power that's needed is the tension force times V, right? So what is that tension force? Well, it has to actually equal Fk. Whoops. It has to actually equal Fk in order to pull it across at constant speed. So that's mu k mg. So the power is just T times V, or mu k mgv, and they put in those numbers and they get 882 watts. Okay, so that's it for chapter 9, and I'm going to post this on the YouTube and follow it up with lectures on chapter 10.